Okay, welcome back, everybody. We're continuing Chapter 5 on forces and Newton's laws, and in this section we're going to look at Newton's second law, which is probably one of the more famous equations that you'll come across, or at least fundamental equations that you'll come across, and maybe we'll even do one, possibly even two examples in this segment as well. Okay? So this right here is Newton's second law. Now, a lot of people kind of say it when it's spoken. They kind of say it in sort of a not so accurate manner. A lot of times people will say F is equal to ma. F is equal to ma. Right? Force is equal to mass times acceleration. It is true, but the bigger idea here, or I guess the greater thing to keep in mind, is that it's not just any force, but it's the net force. You might say it's the sum of all the forces that are acting on an object. So if you apply a force to a mass, it will accelerate. That's what it means. Okay? Newton really said that the acceleration of an object is proportional to the net force. All right? So if we were to take this and say acceleration, okay, net force right here, it's proportional to it. If we were to take that m and move it down, kind of divide it down here away from the acceleration, it is inversely proportional to the acceleration because it's going to come down in the denominator over here. And that should make sense because if you apply a force to something, it will accelerate. But if you increase that object's mass that you're applying a force to, it will accelerate at a lesser rate. Let's say you push on a shopping cart. So your push is your force, the shopping cart is the mass, and so it accelerates at a certain rate. Well, okay, and then you go outside and you apply that same force, you push on a car. All right, much greater mass. Now let's just pretend the car is out of gear and actually can roll, but it's going to accelerate at a much lesser rate. So that's really what Newton's law says. So the acceleration of an object is proportional to the force, or I should say the net force, I should say, and inversely proportional to its mass. And one thing to keep in mind is that the force, being a vector, has the arrow over it, as does the acceleration. And so that means the force and the acceleration are going to be in the same direction. All right, always going to be in the same direction. All right. Well, in many cases, we're going to be talking about forces in two dimensions. And those two dimensions or two directions are the x and y directions. So in the same way that we treated kinematics in x and y independently, the same thing is going to be true of forces. Treat each direction independently. And in most cases, I'm going to use green, so force in the x direction. Green for x, I'm going to use blue for y, forces in the y direction. I should draw an arrow over that force right there. Okay. You can see that we have our acceleration in the x and acceleration in the y. Well, this is very much like in kinematics. You remember writing acceleration in the x and acceleration in the y independently of each other. Same is going to be true of forces. All right, so just one thing to keep in mind. So when we have a force, we have a problem dealing with forces in various different directions, we should set up a table. Now, one of the first things we want to do is sketch a free body diagram. All right. In a lot of cases, this is a very simple thing. I usually like to make mine a little bit more detailed because I just like to draw myself. So you want to label all the forces that are acting on that object. All right. If all the forces are not directly along a certain axis, include an angle. So for example, let's say we have a box right here. You know, I should make that something other than green. All right. Let's just say we've got, there's the ground right there. All right. And we've got a brown box that is going to be sitting on the ground. Okay. And there's a force acting on it like that. Okay. I shouldn't have made that green either. Darn it, because that's not X or Y. That's just a force. I'm going to make it red. All right. There's a red force acting on that object right there at some angle. So what you need to do is you need to take that and resolve that into an X force and in a Y force. All right, so it's got an X component and it has a Y component. This is why our study on vectors and breaking vectors into x and y components is so important, because you're going to be doing this with forces a lot. All right? So, net force in the x, net force in the y. Now, I didn't label all the forces right here, but there's going to be other forces like the weight force. All right? The weight force of the box is going to be something called the supporting force or the normal force acting upwards right here. So you're going to be drawing forces all over these free body diagrams. You want to be able to keep the x's separate from the y's, and that's the idea right here. Okay, so list all of your x direction forces, list all of your y direction forces, and keep in mind they are direction dependent because force is a vector. All right, so it could be, if this one's positive right here, positive y, that's going to be negative y, and that's going to be negative y too. Maybe this might be positive x. Going the other direction might be negative x. So keep those in mind because all those forces are going to be acting on that object. And in some cases, you may even need to resurrect some of your 2D kinematic equations because, after all, we have an acceleration taking place. Right? Net force is mass times acceleration. And acceleration can be described in terms of things like initial velocity, final velocity, time, displacement, so on and so forth. So the fact that we've got acceleration tied to forces, that is what brings all of kinematics and relates it to forces. All right, and we'll look at that a little bit later when we get into some examples. First of which is actually right now. So we'll do one, maybe two examples here, and then that'll be it for the segment. Okay. So first thing I'm going to do, I'm going to shrink this down a little bit because I'm going to need a little bit more space. Okay. So we have Moe, Larry, and Curly, and if you know anything about the Three Stooges, that's the Three Stooges, all right? And so they are, I'm going to move this kind of up into the corner here like so, okay? They are trying to push a boat, oh, I'm moving that around, that's not good. They're trying to take a boat and move it along a dock, okay? And so, let's see here, do that, will it move? No, I'm trying to get this thing to keep from moving because, just lock it. There we go. Okay. They're trying to move this boat along a dock like so. I drew that on that. Okay. In this first scenario right here, I keep drawing on my, I'm sorry guys. I'm going to do this. There we go. In our first scenario, they're all applying a force in the same direction. We've got a force from Moe, force from Larry, and a force from Curly right here. All right. In the second scenario, they're actually opposing forces because Three Stooges, in typical knuckle-headed fashion, don't always tend to work together. All right, but let's write all of our forces. Okay, so in this first scenario right here, they are all in the x direction. So we can say that the force from Moe, all right, so we've got the force from Larry and the force from Curly right here are all going to be in the same direction. And what are they each? Well, they have an 80.5 Newton force that they apply to the boat. Okay, so 80.5 newtons. Again, a newton is about a quarter of a pound. 80.5 newtons and 80.5 newtons. Now, you might be saying to yourself, why write all this out? This just seems so repetitive. I'll fix that 5 right there. These aren't always going to be the same forces, and so writing them out and keeping them straight from each other is going to go a long way to making these problems easier to do. All right, so our three forces are right here, and I made them all positive because the assumption, well, with that is that this is the positive x direction. Okay, so we've got our three forces. What else is going on right here? Well, we have the boat that has a certain mass, right? And here's our mass. The mass of the boat is 752 kilograms. All right, so the mass of the boat is going to be 752 kilograms. In many cases, I'll put MB here, B for the boat. There is only one mass that is being moved right here, but in many cases in the future, we're going to have to put subscripts to keep our masses straight. All right, mass of the boat. They all apply an 80.5 Newton force parallel to the dock in the positive x direction, we'll call that. And part A is, what is their acceleration? or you might say the acceleration of the boat. Okay? Well, let's write down what we know about Newton's second law. We can say that the net force on an object, and in this case the object being the boat, and I'll draw a little arrow over the force right there, is going to be the mass of the boat times the acceleration. Okay, so that means then the acceleration of the boat is going to be the net force divided by the mass of the boat. Well, what is the net force? We have the net force written here as a statement. You might say as a global statement. The net force on an object is always mass times acceleration. Well, we're also going to write this, the net force, as you might say a component statement. We might state the net force in terms of the component forces that add up to it. All right, so the net force on the object, while it's true that it equals mass times acceleration, it's equally true, and I'll draw a little connector right here. These two statements are equally true, that the net force on the boat equals the sum of all those forces. Force from Mo, force from Larry is next, and then from Curly. Larry, and then force from Curly. All right? So that is what? 80.5 plus 80.5 plus 80.5 newtons. Okay, so what is 80.5 times 3? I get 241.5. All right? 241.5 newtons that they are all applying together in the same direction. All right, so that means that's going to be this right here. In fact, let's dotted line box that. That's going to be this net force right here. Oh, sorry, this net force right here that we use to solve for our acceleration. All right, so solving for our acceleration right here, that's going to be net force, which is 241.5 newtons all over the mass of the boat, which is 752 kilograms. And that's going to give us our acceleration. So that divided by 752 is going to be 0.321 meters per second. That's going to be our acceleration of the boat. Not very fast, but keep in mind each guy is applying only about 20 pounds of force, or 80 newtons of force, and the boat is pretty massive, and so it's going to move slowly. So it's not going to accelerate at a great rate, but it is going to accelerate at that rate. All right? Well, in the space that I have left, let's see if I can do part B. Part B, all right? Well, in part B, the difference is, like I said, knuckleheads that they are, the Three Stooges are not working together right here. You've got Mo. So let's do part B. I'm going to draw a line up at the top right here. So for part B, well, I'm not going to draw B. I'm just going to make it a different set of scenarios. The force that Mo, the guy in green, is applying is still in the positive direction, right? So the force from Mo is going to be 80.5 newtons. Okay. However, Larry and Curly are working against him. The guy with red hair and the bald guy. So we're going to say the force from Larry is going to be negative 80.5 newtons, as is the force from Curly. Negative 80.5 newtons. So when we add up our net force, that is the sum of all these component forces, we're going to get something very, very different. Okay, I'm going to see if I don't know if I can move some of these things around or not. I might be able to have space. All right, so for part B right here, right down at the bottom, the net force, it is still true the net force on that boat equals the mass of the boat times the acceleration. But more importantly, right now we want to find out, what is that net force? Well, it's the sum of all the forces. Okay? So just as true is the fact that the net force on the boat equals, and I'll write this in green as well, 80.5 plus negative 80.5 plus another negative 80.5 newtons. I should have written those units right there, but they are units. Okay? Well, what's it going to add up to? Well, you can probably see where this is going. The first two, you guys are going to cancel out, right? And so the net force on the boat is not in the positive direction at all, right? But it's actually to the tune of negative 80.5 newtons in the opposite direction, right? I should say in the negative direction. So they're not being very productive if they want the boat to move forwards. Okay, but like I said, they are the Three Stooges. So let's find our acceleration. The acceleration for part B, once again, is going to be the net force on the boat divided by the mass of the boat. Okay, in this case, so it's going to be negative 80.5 newtons divided by, what is it, 752 kilograms of mass. And that will give us our acceleration for part B. So what do we get there? I get a grand total of negative 0.1, that's not very good, 0.1, negative 0.107 meters per second squared. Oh, you know what? Sorry, up here, right here, I forgot my meters per second squared, right? I got my meters per second, should be meters per second squared. Because after all, it is an acceleration, right? So yes, it is accelerating. First of all, not accelerating as quickly, and by the way, it's accelerating in the wrong direction. But again, what do you expect when you get the Three Stooges? So that's our first application of Newton's second law. And this is going to be a big thing that I'm going to stress a lot, to always write down that what is, again, universally true, the net force is the mass times the acceleration on an object. But also, to state the net force in terms of the component forces that are being added up, either positive or negative, to whatever net force that's going to be. Set them equal to each other, all right, and then you can plug this net force in for the net force that was stated as mass times acceleration. All right, so that's example 5.1. I think we're going to stop right now, and we'll pick up in the next video with example 5.2. Thanks for following along. I'll see you on the next one.